Hello statistics students, my name is Emigh, and this video starts our discussion on chapter 11. Title is Goodness of Fit and Contingency Tables. We're going to start with what is called a goodness of fit test. What that test does, it checks if what we observed is what we expected to observe. When we set up our null and alternative hypothesis, the null is going to be the frequency counts agree with what the claim distribution was, and the alternative hypothesis, sub 1 or sub A, depending on your notation, will be that the frequency counts do not agree with the claim distribution, and nothing else, okay? So agree for null, do not agree for alternative. We're going to use the capital O to notate everything we actually observe, whereas we're going to use capital E for what we expected the outcome to be. Lowercase k is going to represent the number of categories. Lowercase n is going to be the number of trials. And k minus 1 will be our degree of freedom. Now, by expected to observe, if all expected frequencies are assumed equal, that means that we would expect to see a uniform distribution. So our capital E would be our number of trials, lowercase n, divided by however many categories there are. The other option is if all our expected frequencies are assumed not to be equal. In that case, we would not expect to see a uniformly distributed set of observations. Capital E in that case would be equal to the number of trials times each trial's probability of success for each category. StatCrunch has a program that is called Goodness of Fit Program, and if we use it correctly, then we're going to have a p-value. If that p-value is low, we get to conclude that it's not a good fit. And if our p-value is high, we get to conclude that it is a good fit. Please note that the chi-squared, this is the Greek letter right here, chi-squared, goodness of fit, those tests are always right-tailed tests, and that is important in this summary right here. P is low, not a good fit. P is high, good fit. Let's try one. A random sample of 100 weights is obtained. The last digits of the weights should occur with the same frequency and fit a uniform distribution. Weights, when reported, not actually measured, tend to end in a 0 or a 5. Test the claim that the weights in this table were not actually measured, and they do not fit a uniform distribution. They want us to choose a significance level of alpha equals 0.05. All right, let's just talk about this for a second. So if someone asked you, how much do you weigh? Apparently there's a tendency to just round our number, just approximate it to something that ends in a 0 or some weight that ends in a 5. But if those weights were measured, then all the last digits, we should expect them to show up of equal frequency. Well, looking at this table here, oh wow, check this out. 46 weights were reported with a ending in a 0. What that means, you guys, is these were self-reported. There are only 100 of them. There's no way 46 actually end in a 0. Only one ended in a 1, 2 in a 2, 3 in a 3. 3 of them ended in a 4. 30 of the weights recorded ended in a 5. 4 ended in 6. 0 ended in 7. 8 of them ended in 8, and 3 of them ended in 9. So we would expect all these frequencies to be the same number, but we can clearly see that they're far from it. And so just eyeballing it, I'm going to say this is not a good fit. But let's find out how we calculate that. We set up our null hypothesis as the probability of the weight ending in a 0 being equal to it ending in a 1 being equal to ending in a 2, all the way. See, they're all equal, okay? Null hypothesis, all equal. The alternative hypothesis would be that at least one of the possibilities is different. If we get even just if I put a does not equal right here, that would be at least one of the probabilities is different. All right, we are going to run this in StatCrunch with a warning first. This first column of data, it looks like quantitative data, like quantities, numbers. But warning, these are actually the categories. These right here are the frequencies, the tally marks, the counts, okay? So just heads up for that. Don't accidentally use the categories as values, even though sometimes the categories are numbered. Okay, so what we observed is this list here, okay? This is going to be the capital O, observed for list 1. And then what we expected to observe, we will find by capital E, is the number of trials divided by the number of categories. Okay, so we had 100. That was right here, you guys. N equals 100. That's N. Number of categories, that's these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 categories, okay? Ooh, 10 categories for K equals 10. So capital E, or what we expected to observe, would have been those 100 weights divided equally into groups of size 10. That would be 10 in each. So we should have got 10, 10, 10, 10, 10, 10, 10, 10 in this column here. All right. Oh, showing the answer already. Let's go to StatCrunch and run this. Okay, once we open this in StatCrunch, notice we've got the categories here and the observed frequencies here. Go to Stat, and you'll see the goodness of fit test right here, and we are running the chi-squared test. Open that program. Doesn't need much from us. Look at this input screen. It's very simple. It wants to know where our observed frequencies are. So we're going to tell the program we put the observed frequencies in the, not the categories, in the observed frequencies column. Okay, the next thing the program needs to know is, well, what did you expect to observe? And then we'll see if those fit together. Okay, well, what we expected to observe isn't here. It's not in the categories. It's not in the observed frequencies. Remember, what we expected to observe was 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. So that right there is what we expected to observe. So you could type it in manually. We got this from 100 trials divided by 10 categories equals 10 each. You can type that in manually and then tell it, okay, I typed it in right here, var 3. But you don't have to. The program can do that division for us if we just tell it, hey, we expected all cells to be in equal proportion. What that means right there, you guys, is that we expected a uniform distribution. All right, let's see if what we observed fits what we expected. Okay. Oh, and look, this is nice. It even shows you that all 10s for the expected. Capital N, degree of freedom. This is our test statistic, should you need it, 212.8. And we're going to use the p-value right there, 0.00001. It says that. Okay, we are going to compare that p-value to the significance level, alpha, 0.05, and we have a lower p-value than the significance level. If p is low, the null must go. We reject the null hypothesis. Or based on the summary from the last slide, you can jump straight to, if p is low, not a good fit. We say there is sufficient evidence to support the claim that the sample does not fit a uniform distribution. What this means is that we have evidence that the weights were reported and not actually measured. All right, and there's an example of a goodness of fit test. Let's do one more. A slot machine is tested by playing it 1,227 times. There are 5 different categories of outcomes. When testing the claim with the 0.05 significance level that the observed outcomes agree with the expected frequencies, the author obtained a test statistic of chi-squared equals 8.903, and then we're just asked, does the slot machine function as expected? It's not obvious, but we have to interpret that as, that they're asking us to see if what we observe is what we expected to observe, and that is called a chi-square goodness of fit test. The test statistic given to us was 8.903. That was given, okay? The critical value is 9.488, and we would find that at the intersection of the degree of freedom and the significance level on the table. I showed you how, if you need that particular I showed you, I think, last section. If you need a particular table for a question, the link for it will be right there. And remember, it's a pretty straightforward table. Just look for the intersection of, the last one was N and alpha. This one is DF and alpha. All right. And we can also use the StatCrunch program, if we'd rather, using a program here called Variance Stats. Either way, we'll get to the 9.488. Had it been on the table here, degree of freedom was 5 categories minus 1, so 4. And then significance level alpha was headed this way, this way, this way, right there. There's that 9.488. It's just a little snapshot of the table that'll be available for you if you need it. Or, of course, like I said, you can use variance stats. Okay, went ahead and sketched a chi-squared distribution. Notice that it is all in quadrant 1. And based on, we got to put some labels there before we just put the answer. Okay, we know that all chi-squared tests are, look back right here, you guys. Chi-squared goodness fit tests are always right-tailed. Okay, so I'm going to take that graph and I'm going to cut off the right tail. Okay, left, right, this side. Cut it off. It always gets cut at the critical value from the table. The critical values, those existed on the tables. They existed before we've gathered any data. The test statistic, on the other hand, wasn't calculated until we went out and tested these 121,227 times. And the test stat we came up with was 8.903. This is a standard number line. 0 is here. So 8.903 would be somewhere on this side of 9.488. So our test statistic of 8.903 ended up in the fail to reject region. Okay. Wow, this really looks like they're the same number. I don't want that. I'm just gonna, this one right here is the critical value. This one right here is the test statistic. Okay, that's better. Had the test stat ended in this little region, we would have rejected the null hypothesis, but it didn't. It's in this region, so we will fail to reject the null hypothesis. If we fail to reject the null hypothesis, we say there is not sufficient evidence to reject the claim that the observed outcomes agree with the expected frequency. Therefore, the slot machine appears to be functioning as expected. Okay. Chapter 11 has a second test. So they have we have the goodness of fit, chi-square test in Chapter 11, and we also have the test of independence. Test of independence checks if the rows and the columns in a contingency table are independent of each other or not. We'll set up the null and alternative hypothesis, where the row and column variables are independent for the null hypothesis, and the row and column variables are dependent for the alternative hypothesis. Requirements for this test. The sample data are randomly selected. They are represented as frequencies in a two-way table. That means they're columns and rows. I'll show you one in a second. For every cell in the contingency table, the expected frequency is at least 5. O is going to be the observed frequencies. E is going to be the expected frequencies. R is going to be the number of rows. C will be the number of columns. The degree of freedom will be the number of rows minus 1 times the number of columns minus 1. And we are going to use a StatCrunch program called the contingency program. All right, so a lot of words in here. If you get a contingency table, then we're checking if the rows and columns are dependent on each other. That's why it's called a test of independence. The StatCrunch program, though, is called the contingency program. All right. Tests of independence are always right-tailed, so that's cool, just like the last one. And the summary, if you're just jumping straight to it, would be if you get a p-value lower than your significance level, we would say that the rows and columns are dependent on each other somehow. And if we get a p-value higher than the significance level, we will conclude that the rows and columns are independent of each other. Let's try one. Test the claim that a successful recovery of a knee injury depends on the type of treatment a patient receives. Test if the row and columns are independent of each other. All right, so this right here is what we call a contingency table. See, it's got rows and columns. So we're basically checking, did these columns, the success and the failure, did they depend on these rows? So this person had looks like 66. 66 people had surgery. 54 ended in success. 12 ended in failure. Another group of patients, looks like 92 of them. They wore a weight-bearing cast. 41 success, 51 failure. Next group of 73, non-weight-bearing cast for 6 weeks. 70 success, 3 failure. That looks good. This one's looking nice. If I saw this table and I had a knee injury, I might be like, oh, this looks good right here. Maybe we talk about a non-weight-bearing cast for 6 weeks. There was one other process, though, or treatment, I should say. It's a non-weight-bearing cast, but the patients wore it for less than 6 weeks. Still 17 successes, but 5 failures that time. They were at less than 6 weeks. So our job is to check. We get to crunch these numbers. Does success or failure depend on the treatment type that the patient received? All right. Our degree of freedom is going to be 4 rows minus 1 times 2 columns minus 1. Multiply those together and you get 3. Null hypothesis is set up as if the rows and columns are independent of each other. Alternative hypothesis is set up as if the rows and columns are dependent of each other. When we run the program, which we need to do, it looks like we're going to get a low p-value. Let's go check that out. Okay, when we get to StatCrunch, we go to Stat, and we're looking for the program called Contingency, but we won't see it here. It is a subgroup of tables. So go to the Tables menu, then Contingency, and we're going to run this program based off of the summary of the data that we were given. Open that program. Okay, check out the input screen. It's got var1, so just looking at our data here, var 1 is just the titles of the rows. var 2 is one of the columns, and var 3 has the other column. So careful with this one. It says select the columns. So we have to tell them, okay, the columns are in var 2. I personally have to hold shift, down arrow. So I say the columns are in var 2 and var 3. Next thing the program needs to know is, okay, well, where are your rows labeled at? The row titles are in var 1. Okay, so careful setting that up. Once you get that, though, you don't have to worry about any of this other stuff. Just compute. Okay, on the output screen. Looks good. A couple things we need are down here. Degree of freedom is 3. The test value, should we be asked it, is 58.39. And the p-value is once again very low. It's less than 0.0001. So we're going to have a low p-value again compared to the significance level. And that's where that p-value of 0.0000 came from. Less than significance level, which is the default, 0.05. P is low. If we jump straight to it, summary from the last slide, P is low. The rows and columns are dependent on each other. So we would say that there is evidence to support the claim that success is dependent on the treatment type. Now the test, it does not tell us which treatment is best, but we could calculate the success rates. So if you're asked, well, what is the success rate for surgery? It would be 81.8%, and you could calculate that by, you just need to know the total number that had surgery. So 54, 60, 66 had surgery. So if you did, for surgery, if you did 54 successes out of 66, then that will come back with 0.818 approximately. And then you'll multiply that by 100, and that is where this one came from, okay? So if you're asked the success rate for each of the types of treatment, you could do that. I'll show you one more. For the weight-bearing cast, it would be, let's see, we had 92 in that group. So we would do 41 were successful out of the 92 who tried that treatment type. It would output for us 0.446 approximately. Multiply that by 100. Okay, move the decimal 2 places, and that's where the success rate for non-weight-bearing cast is. Here's the success rate for non-weight-bearing. 44.6 was the success rate for a weight-bearing cast. 95.9% was the success rate for the non-weight-bearing cast for 6 weeks. And 77.3% success rate for the non-weight-bearing cast less than 6 weeks. All right, so that information might be helpful in to a doctor or patient or someone in this situation. Chapter 12, title is Analysis of Variance. It's often just called ANOVA, A-N-O-V-A. What it does, it tests if 3 or more populations have equal means. For example, if alpha equals 0.05, we're asked, do the samples come from populations with the same mean? Okay, well, let's see our data here. We've got IQ scores of children. I think we've seen something similar to this with the lead levels. So the first group here, they had low levels of lead in their blood, and these were all of their IQ scores. Okay, so this is the we'll call that population 1. Population 2, we've got some IQ scores here for those children that had medium levels of lead in their blood. And then we have some IQ scores for those children that had higher levels of lead in their blood. And so what we're asked is, hey, is the average IQ score the same for all three populations? Okay, there are a lot of numbers here. We want to know, is the average IQ score the same? We say that as, are the means the same? So that means we would run an analysis of variance or test of ANOVA. Null hypothesis is going to say, all right, those means are all equal. And alternative hypothesis is going to say, okay, at least one of them is different. We're going to run a StatCrunch program called ANOVA. Let's open that. Well, let's see. Hold on. Okay. This right here, you guys, I would have to hand type into StatCrunch manually, which I don't want to do. So when you guys do your exercises, your data will populate into StatCrunch automatically. So when you get the data already populated into StatCrunch, the program ANOVA is pretty simple to find. I'll show you where it is. Okay, like I said, when you get to StatCrunch, your data will already be populated here. You'll go to Stat, and ANOVA is right here. In this class, we do one-way test of ANOVA. So we'll open that program. And the input screen is really simple. It just needs to know from us the columns, which will already be there for us, okay? And then when you hit compute, which mine has no data, so it won't run the program. But if I were to have that data in there, or will be F, capital F. That's the test statistic for an analysis of variance. So for this particular set of data, it would be 4.0711222103 and so on. The p-value that it would output for us would be 0.0195. We would just compare that p-value to the significance level as always. And it turns out here we have a low p-value once again. If p is low, the null must go. And that means we are going to conclude that these populations have different average IQ scores, different means. So we would say that there is evidence that the three samples come from populations with different means. Okay, another summary of this from StatCrunch, or manually you could, should you be asked, like, well, what's the sample size? There were 78 in that low lead level, 22 in the medium, 21 in the high. X bar would be each of their averages. These are our mean IQ scores. 102.7, 94.1, that's a pretty big drop. And then 94.2, those two are pretty close. Actually, this one was higher than this one here. Standard deviation also needs to be considered. 16.8, 15.5, 11.4. It appears that greater blood lead levels are associated with lower IQ scores. All right, that will finish our course material. My name is Jami Emigh. Thank you for being here, and I will see you sometime soon. Have a good day.